Okay, hi everyone. We're 1 minute past the hour, so we'll get started. I hope you're having a productive start to your 2020. And welcome back to the ENLA seminar. We're scheduled to have a talk now every fortnight until about mid-April. I'm Alex Townsend at Cornell, and I'll be chairing the session today. So our inaugural speaker for 2022 is David Bindel, who is a superb colleague because he's also at Cornell University. He's an associate professor in the computer science department and a well-known researcher to many of us on this call. His research is like breathtakingly broad and focuses on applied numerical linear algebra and scientific computing. He also does lots of applications in various types of science and engineering problems. He has, of course, been awarded many prizes for his research, including like the Sloan Research Fellowship, the Householder Prize, SciGES Featured Paper, the SciG LA Prize, and that's the only ones that come to mind. I'm sure there are many more. Right now, he's the director of the Center for Applied Maths at Cornell and the Associate Dean of Diversity, Equity, and Inclusion. So it's a great pleasure to introduce David Bindel, who will be telling us about induced point approximations of kernel matrices. Thank you, David.
Thank you for the kind introduction, Alex. And I think your first comment of welcome to 2020 is on point in some ways. It feels a little bit like it. But to all the rest of you, happy 2022 and good morning, good evening, good afternoon, wherever you happen to be in the world. The talk title actually is is slightly off for reasons that you'll see as the talk progresses. So today what I really want to talk about is inducing point approximations with kernels. And we're going to tell a few stories about how we get to those approximations, some of which focus on the matrices, some of which focus on other aspects of the approximation. So there's actually less research in this than I had originally planned. I got enthusiastic about telling several of the different themes, and the research papers that I had hoped to get to sort of incrementally got bumped out as I expanded the story. But there are a number of people who have helped me get along this road. Some of my students, colleagues, former students and colleagues who are now at other places. And my bunnies have probably heard more about this than anybody else because I do talk to them when I'm at home in isolation. So the setup for today is that we're trying to do function approximation from sample values. So we're given some evaluations of a function f at points x in a domain omega. I'm typically going to assume omega is a compact domain. I don't think it matters very much for things that we're talking about today, but for some it might. Subset of d-dimensional space, let's say. And we're going to stick for today with the single output case, although multi-output approximation is also interesting. And so what we want to compute is an approximator to our function f, and the star of today is going to be a class of methods called kernel methods. And kernel methods are great mathematically for a number of different reasons that we'll see, but they do have some challenges. One is you have to choose this fundamental object that's in the middle of the method called the kernel, and it's not always obvious how to do that. Once you've chosen that kernel, you have to try to reason about the approximation properties, unless you want to drive blind. And there's multiple frameworks for doing that, and they interact in interesting ways with methods that approximate the kernel system. And then we want to compute quickly with large amounts of data, and that could be very challenging with these methods because if you do the things in the most naive way, you're working with a dense n by n linear system. Fitting the approximation costs order n cubed. Evaluating at a new point costs order n. And evaluating the uncertainty, depending on what you've done, will typically cost order n squared. So these are things that you want to do fairly regularly. And if n is a million or a billion, you might be very unhappy with this. And so what we're really about today is, can we get around that bottleneck? And there's a number of different ways that people have thought about to approach this computational complexity issue. And we'll focus on one specific family that involves choosing a subset of the points, or a subset of points in our domain, called inducing points. So the plan for today is, I'll tell you a little bit about the basic setup. That's mostly done. And then we'll talk about three different perspectives on kernels. So the first one is the one that I think is the most naturally numerical linear algebraic. This is the one that actually got me into this space. So thinking about approximating kernel matrices, and maybe we'll sneak a little bit into functional analysis land there, but it will be very much a linear algebra perspective. And then I want to switch gears and talk about two other perspectives that give you different ways of thinking about the approximation process. One coming from statistics, so this is the Gaussian processes perspective, and the other one coming from approximation theory, and this is the optimal recovery perspective. And in each case, there's sort of a basic picture that I want to explain to you, and then I want to tell you a little bit about how people think about inducing point methods in these contexts. And part of the reason that I wanted to set things up this way is because I feel, at least, like there's been a lot of research on each of these things individually, but there aren't a ton of people who draw connections between these different domains, and there are a lot of connections to draw. And this is something that makes me really excited, and I wanted to convey some of that to you today. So our key idea is going to be that we'll organize our approximate methods around a subset of points, or not necessarily a subset of the points x, but a small set of points in our domain omega. And these are the inducing points. And just to give you a preview of what's to come, the three different perspectives that are going to give us three different methods. For the numerical linear algebra perspective, we're going to talk about low rank approximations. I'm going to focus on the subset of regressors and fit-C methods. These are not things that I had anything to do with inventing. There's a classic textbook by Rasmussen and Williams that does a good job of describing these, but I want to tell you a little bit about it from the numerical linear algebra perspective and say a little bit about what I have done with it. And then we'll talk about some work on variational inference methods for sparse Gaussian processes. And then I'll talk about the thing that I'm really most excited about, which is an extension of the optimal recovery perspective from approximation theory. Okay, so I've told you this in words. Let me tell you now in pictures. There's three different perspectives, but I really think there's four different stories that we tell about how you come about, or how you come to kernel-based regression. Two of them I think of in very much linear algebra facing terms, and two of them I think of in optimization and statistics terms. Okay, so the first story that we're going to tell is one that's fairly familiar. So you're interested in mapping a function or approximating a function, say on R2, and you say, maybe I want to approximate this by quadratics or something up to quadratics. And so I'm going to say, I've got a basis that consists of the function 1, x, y, x squared, x, y squared. Or I can think of, I'm going to, for any given point in my space, have a map to this higher dimensional space called a feature map, which I'll denote by psi. And I'm going to have now a simple linear model for my function in that feature space. So it's some linear combination of the features, and that's my approximator. Now, I write this example in the case where I've got a finite number of features. More generally, you can think about having this feature map go into some abstract Hilbert space. It doesn't have to be finite dimensional, but I do want an inner product. And we've got now a linear map on that Hilbert space, so an inner product between some representation vector D and functions that we're going to use as approximations. So if we have a small number of features, then usually we're in the land if we've got ample data of either underdetermined systems or interpolation. So if we've got more data than we have features, then we do least squares. This is sort of the standard thing. If it's equal, then we can do interpolation. But there's a tricky challenge here, which is one of the things that motivates people to think about kernel methods, which is if you're in more than one spatial dimension and you're doing general approximation in RD, you might get unlucky about where you put the points such that your approximating system is ill-posed. There's always examples of this. This is the Merhuber-Curtis theorem. So you have to be careful not just with how you construct your space, but with how you sample the space as well. Of course, if we have more data or more features than we have data, then we can no longer uniquely find a minimal norm or minimal error solution. Instead, we've got in general, a family of solutions that will interpolate, or a family of interpolators. And what we're going to think about is solving the underdetermined problem in a minimal norm sense. So for a standard inner product, if we were thinking about this as just being matrices, we would say the way that we're going to fit things, if our vector of evaluations is y, is to compute the pseudo inverse, which in this case looks like A transpose inverse. So you've got a gram type of matrix times y, that gives us our coefficient vector. But then we always evaluate our approximator by dotting that coefficient vector with another kernel vector. So you get your D, you dot it with a feature vector, and that gives you your approximation at some point. So one of the things to notice about this picture is that we've got many different models that approximate our function. And implicitly in the construction of this underdetermined system, we're saying we prefer some models to others. So there's some notion that there's a bias in how we construct our approximator. And part of our goal is to understand how to best choose those biases. So if you have seen kernels in the context of somebody trying to teach you machine learning, they will probably have told you about the kernel trick. And the kernel trick is just the observation that when you do this minimal norm solution trick, and now say, evaluate the minimal norm solution at a point, the formula that you get involves only inner products between feature vectors. So if A transpose is a matrix whose columns are feature vectors at each of my sample points, then A transpose is going to be a matrix of inner products of feature vectors at different sample points. And this psi of X transpose A transpose is a vector of inner products of a feature vector at my evaluation point and feature vectors at each of my sample points. And so we call this inner product of feature vectors a kernel. If you have a feature map, the kernel is just defined as the inner product of the feature map at one point and the feature map at another point. So it's a symmetric bivariate function, positive definite for most of the things that we're going to talk about today. As a piece of notation, and I'll remind you of this a couple of times later, in general, when I have a matrix where I'm evaluating I'm evaluating the kernel at pairs of points, I'm going to denote that by this subscript notation where I say subscript capital X is the sets of points that index my rows. The second capital X tells me about the subset of points or the set of points that index my columns. And each entry is going to be an evaluation of my kernel function at a given row and column or at a given pair of points. So the computation in terms of this feature map, or in terms of this kernel trick rather, I'm now going to think of a different set of coefficients. So rather than the solution to my minimal norm problem, I'm going to break off this A transpose piece involving just the kernel matrix. I'm going to say solve the kernel system kxx times c is equal to y. Y is going to be f subscript x in this case corresponds to evaluate my function at each of the data points x. And then the approximator is going to be this function s, which is take a dot product of the row vector, which is the row of kernel evaluations where the first argument is the evaluation point, and the second argument is each of the interpolation points in turn, and multiply that by this coefficient vector c. Or expanding things out, you've got this sum of kernel functions. Okay. So yes, so there's an excellent question in there in the chat about, am I thinking about these as quasi-matrices? The answer is absolutely yes. So when I draw things in matrix form, that's the way I think about it, because I draw infinite things by small boxes, but they are indeed potentially infinite dimensional objects. Okay, so the story that I've told you so far is very linear algebraic and is focusing on these feature vectors, which you can think of as rows in an underdetermined system. But there's other ways of thinking about things too. I could also say each of the features is itself a basis vector for some space, and I'm looking within this space for approximators. So the question is, do you think about your matrix in terms of rows or in terms of columns? If you think about it in terms of rows, that's what I think of as the feature map perspective. If you think about it in terms of columns, this is the feature vector or basis vector perspective. And we're going to now introduce a concept of a particular space, which is the native space, that's spanned by combinations of these basis vectors, or the combinations, you have a coefficient vector d that lives in this Hilbert space, if you like. And in general, we're going to be able to form our approximations, and this is a theorem, by saying that we look at the feature vectors just associated with, or we look at a set of feature vectors that are just associated with kernel evaluation, so kxxi. So we've got a, if you like, a data-dependent basis. And that's another way of thinking about the construction of these kernel approximations. Now, I don't really want just to have a space. I want to have a space with some structure on it. And so I'm going to define a Hilbert space by saying, let's think about the expansion in terms of these feature vectors or basis vectors. And we're going to say, call the feature vectors an orthonormal basis. So calling them an orthonormal basis gives us a geometry, gives us a Hilbert space structure. Now, because they're an orthonormal basis, we can say the norm of our function s in this Hilbert space is going to be the norm of the d vector in the coefficient Hilbert space. And this Hilbert space has some nice properties. In particular, it's what's called a reproducing kernel Hilbert space. So this is it's an abstract space, potentially infinite dimensional, which means that you may or may not be able to evaluate functions at a point as a bounded functional. But in a reproducing kernel Hilbert space, you do indeed have a bounded functional that's associated with evaluating at a point. And you can define that bounded functional in terms of these feature vectors, if you like. So if you write down this construction, then this function k sub x defines a point evaluation functional where you take an inner product of that functional with your with your S, your approximator, in the Hilbert space, and it recovers evaluation at a point. Okay, so we've got now a matrix perspective, and we're starting to creep into a functional analysis perspective on how we think about this. And that functional analysis perspective will become more important a little bit later on. Now, so far, I've said everything assuming that there's a feature map in the background. But if I don't have a feature map explicitly, I can still build all of the machinery that you've seen so far. So suppose that I have a symmetric kernel function. So it's mapping my domain cross my domain into R. We call this kernel function positive definite. If anytime I form a kernel matrix, it's symmetric and positive definite, as long as I choose independent points or unique points, X. So I'm going to associate to my kernel an integral operator. So script K takes functions F into new functions by integrating the kernel against my function F. And if I've got a continuous kernel, sorry, I dropped, no, I still have continuous there. So I'm going to assume a continuous kernel. Assuming that I've got a continuous kernel, I've got a compact operator, Hilbert-Schmidt for everything we care about. And so we're actually going to be able to apply Mercer's theorem and write down a nice convergent approximation in terms of sum of lambda j, psi j star. So the psi j's are going to be my eigenfunctions. The lambda j's are going to be my eigenvalues. And now I can say, let's define features as square root of lambda j times psi j. And it turns out that those are perfectly good features for building my feature map. And if I go through all of the machinery that I've talked about so far with those features, then I get a reproducing kernel Hilbert space where the kernel is this K that I started with. So we saw that for the computation, you don't need a feature map because there's this kernel trick. It turns out that you don't even need the feature map in the background. If you really wanted one, you could reconstruct one using the ideas from integral equations or this decomposition of an integral operator. Okay, so we're going to focus today on things where we've got a positive definite kernel function. I might slip sometimes and call it the covariance function. That's if I'm in my Gaussian process headspace. I'm going to cheat a little bit. I will have some pictures at least of a conditionally positive definite case, but you should think for everything that I'm writing equations about that our kernels are going to be positive definite today. And for the most part, if I'm talking about concrete choices of kernels, I will also assume that they're stationary and isotropic. And those two things together mean that the evaluation of the kernel, yes, it depends on X and Y, but really it only depends on the distance between X and Y. And because it depends only on the distance between X and Y, if you look at K of X, Y, where Y is fixed and X is varying, you get something that's radially symmetric about that center point. And so these are sometimes also called radial basis functions. So there's some common examples that are used in statistics. There's additional common examples that get used in approximation theory for reasons that I haven't fully understood. Those two sets don't always overlap each other. So the statisticians really like Matern and squared exponential types of kernels, but tend not to use things like inverse multiquadrics. Even if I've chosen a family of kernels, there's often some additional parameters that I have to specify, like a length scale or an absolute magnitude of the kernel. I'm going to sweep that under the rug today almost entirely. There's a completely different talk about how you do hyperparameter optimization efficiently. But I do want to show you pictures of what some of these kernels look like. So this is the Matern family of kernels that's very popular for statistical modeling. People think about it a lot in geospatial statistics and also in time series analysis. The squared exponential function, which is e to the minus distance squared, with some length scale involved and potentially some absolute scaling involved, is a limiting case of the Matern family, if you like. And people usually think about the Matern functions with these integer plus a half parameters that describe how smooth the kernel is. So you can see in this picture that the Matern 1/2 kernel is pointy, right? So it's continuous, but it's not differentiable at the origin. Matern 3/2 has a derivative at the origin, but doesn't have a second derivative. Matern 5/2 has 2 derivatives, but not 3, and so forth, right? Until you get out to the squared exponential, which of course has as many derivatives as you care to take. So why do I say anything about the derivatives? Well, there's 2 reasons. One is that I referred earlier to this notion that we have a challenge in picking what our kernel will be. And that challenge is partly, how do I pick a kernel that's simple enough that I know how to compute with it and makes some sort of sense for the data? But what does it mean to make sense for the data, right? We really have really strong intuition. And in some sense, any choice that's within this reasonable category, the so-called universal function or kernels, is okay, right? So a kernel is universal if when you throw enough data at it, you can recover any continuous function, essentially, right? But there's lots of kernels that are universal, but are really bad choices for one reason or another, because enough data may be a lot of data, more than you actually have, right? So we really want a kernel that's going to allow us to take a relatively small amount of data and still get a good approximation. And so that means that we're making some implicit assumption in the choice of kernels. And the implicit assumption that we're making in these standard kernels is about how much smoothness we can assume. So if you're looking at something like a squared exponential kernel or a very smooth kernel, implicitly you're assuming that you really, really strongly prefer very smooth approximator functions. If, on the other hand, you're looking at something like Matern 1/2, which isn't even differentiable, you're saying it's okay if my function is not necessarily going to be differentiable itself. And because of that, I might actually need more data to be very confident about my approximation. So the idea that you're going to, in some cases, have a choice of how regular your kernel is, giving you a choice about what you can easily recover or what your inductive biases are, that reflects in the structure of the matrices. And part of the reason that I've been thinking a lot about these inducing point methods recently, as opposed to some other methods that lead to other interesting structures in my computation, is that in many cases with machine learning, you're interested in trying to generalize by a ridiculous amount, right? So you really have much less data than you have any right to try to generalize from, but you're going to generalize anyhow, right? Why can you do that? Because you're intuitively assuming a really strong inductive bias. And the way that that's going to show up in our computations is that the kernel matrices that we form will have a very rapid decay in their eigenvalues. So they're almost going to be singular. And there's going to be a couple of different ways of thinking about this when we get to the error analysis portion of the talk, that I'll come back to. So you basically have that there's some sense in which you're concentrating on this low dimensional set of functions that are smooth, or as smooth as you would like. Okay, so let's be a little bit more concrete about the eigenvalues for these kernel matrices. So the starting point for this is really people thinking about not bounding the eigenvalue decay for kernel matrices, but bounding the eigenvalue decay for these associated integral operators. So you have an integral operator that's defined by a kernel function, and this is a nice enough set of operators where that you can apply the Weil-Courant theorem. And so you can say the n plus first eigenvalue, if you say lambda 1, lambda 2, lambda 3, and so forth are in descending order, this is positive definite, so these are all positive numbers, is going to be bounded from above by the norm, 2 norm, of k minus s, where s is any rank n approximating matrix. So if I can come up with a good low rank approximation to my integral operator, in the sense that there's a small difference, then that automatically gives me bounds on the n plus first eigenvalue of my kernel. And so there's a whole literature of people building decay bounds for different types of kernels typically on the unit interval by the unit interval, because that's the easiest case to work with. So this goes all the way back to Fredholm and Weil thinking about integral equations, and goes all the way into the 21st century. The high-level tactic that's used in a lot of these things is you say, well, let's do polynomial interpolation of my kernel, or polynomial approximation of my kernel, to get this finite rank S. And the question then becomes, how rapidly do my polynomial approximators converge given some nice regularity of this kernel function? And the answer is that if my kernel function is C mu, so I've got some finite level of differentiability, then I converge faster than n to the minus mu, in fact, significantly faster. If it's analytic on some region, on some strip around the real line, then I get exponential convergence. If it's analytic over the entire complex plane, as is the case for the squared exponential kernel, then the eigenvalues decay even faster than that. All of this is for the Fredholm operator. You can actually do a very similar type of construction on the matrices directly. You have to be a little bit careful, but the high-level punchline here is that the behavior for the matrices is very much the same as the behavior for the integral operators, that the eigenvalues decay very quickly, and the rate at which they decay depends mostly on how smooth the kernel function is. Okay, so now suppose that I've got a kernel function that is quite smooth, and I want to solve my kernel system. So I want to solve a system involving this kxx. Well, in practice, I'm usually not going to solve that system. I'm going to solve some slightly regularized version of the system. So I'll add a diagonal term frequently. Depending on where you come from, that diagonal term can be interpreted as a noise variant. So the statisticians sometimes call this a nugget term, which fascinatingly enough comes from the background of this family of methods in geospatial statistics. So when people talk about kriging, Krieg was interested in finding ore. And so the nugget term, when you're doing modeling of a distribution of minerals, has to do with the probability that you will actually hit a nugget of that mineral when you're digging a borehole. You can also come up with non-statistical reasons for adding this regularization term. But what we're going to do is say, okay, we've now got something that looks like this regularization term, which is nice and diagonal, let's say, plus an almost low rank matrix. And what we're going to do is approximate this by something that is exactly low rank, plus a diagonal correction. So the diagonal correction can just be eta I. That's the subset of Regressor's technique. Or it can be eta I plus some piece that's meant to make the low rank approximation plus the diagonal actually agree with my true kernel matrix plus this regularizer on the diagonal. So That sometimes goes under the heading of FITC, which is something independent. I'm blanking on the name. Anyhow, it's essentially diagonal correction in order to get the diagonal of your kernel matrix right. Okay, so now when we started talking about the linear algebra perspective on kernels, I started by saying, okay, we're going to, if you've got a finite number of, or a small number of features, then you do least squares. If you've got a large number of features, you've got an underdetermined system, and you're going to solve a minimal norm problem. Here, we've solved a minimum norm problem involving actually a new kernel that's induced by this subset of points. So we think about choosing the subset of points such that this construction is a good approximation to kxx. Another nice thing about it is it's now clear how you're going to approximate your kernel for a new pair of interactions. So you'll say k interaction of one argument with all of my u points times ku u inverse times k interaction of all of my inducing points with the other argument. And so that gives me my approximate kernel. So I've constructed this low rank approximation, which I can also think of as constructing an approximate kernel. And there's a sense in which I'm still doing this regularized minimal norm solution picture. But as a nice exercise in linear algebra that the last time I taught matrix computations, I actually gave to my students, you can say, what happens if I plug in this FITC or SOR approximation to my kernel matrix into my solver and then try to do prediction with it? And the answer is you can rewrite things in terms of a regularized least squares problem, where what you're trying to do is fit kxu lambda to y in sort of a D-based norm. So you've got a norm that's associated with this diagonal scaling with a regularization term that's associated with your KU. And if you want to, you can actually recover the coefficient matrix C out of this. It's going to be within a scaling the residual of your fit. But you don't actually need the full C vector in order to do further approximation or prediction. You can actually take the k little xu and multiply it by lambda. So if you think about this in terms of this intermediate variable lambda, you can say the intermediate variable lambda is just there as a computational trick to get your coefficient vector in this modified kernel system. Or you can say that lambda actually contains some semantic information. In fact, what you're doing is solving a regularized scaled least squares problem in which now the least squares vectors, your basis vectors, are the kernel basis functions at these inducing points. Sometimes this is good enough on its own. Sometimes this is not enough on its own, but is a pretty good start. And of course, the numerical linear algebra thing to do when you've got a good approximation that isn't good enough on its own is use it as preconditioner, which indeed we have done in some of our work. It turns out that things like log determinants, which are used in hyperparameter tuning, are also very easy to compute in this setting. Okay, how do I choose my inducing points? In the literature in the statistical literature or in the approximation theory literature, people will usually talk about this as some type of greedy heuristic, and then they will write down something that it always takes me forever to understand, and is 95% of the time a restating of what I think of as Cholesky, right? Pivotedcelestia. So how does this work? We're going to think about, we've got our kernel matrix, and we want to choose a set of inducing points such that the approximation based around those inducing points gives us a good low rank approximation. So we're going to start by choosing one inducing point, and that corresponds to choosing one column, and then we're going to do a step of Cholesky factorization. So we compute a Schur complement. In the Schur complement, now all of our diagonal elements get smaller. They continue to get smaller and smaller, approaching zero as we progress through the computation. We're going to take the largest of those diagonal elements, and we're going to move that to the front, and that's going to correspond to our next inducing point. And then we repeat the process, getting more and more inducing points. Because we're doing a left-looking factorization, we don't actually need to compute the full Schur complement at each step. We only need to keep the diagonal of the Schur complement in order to figure out which point we're pulling into our factorization. So this can be done quite efficiently. And if we keep m inducing points, the total cost ends up being order nm squared, and of course, order nm storage. And you can see this is actually the diagonal element magnitudes. This is for a squared exponential kernel, where in 2D, I've got this set of points. And you can see that the diagonal elements, as I progress through the Cholesky factorization, do indeed decay quite quickly. And of course, I can always estimate the nuclear norm, at least, or Frobenius, or whichever of the piece that I'm neglecting by throwing away the Schur complement and keeping only the low rank piece that I've got in my partial Cholesky factorization so far, just by controlling the sum of these diagonal elements. And so once I decide that that sum is small enough, in this case, I think I decided it was, my cutoff would be 10 to the minus 7th, then I quit, and I've got my set of inducing points. Now, of course, the greedy approach is not necessarily optimal, but it is pretty good, and it's a great starting point for algorithms that optimize further. Okay, so this is maybe a good place to pause for questions, or pause to check if there are questions. Not so far. Okay, so let me tell you now about two ways of thinking about these inducing point methods that tackle the problem from a slightly different perspective. One of them tackles it from the perspective of, let me think about being a statistician. The other one tackles it from a perspective of, let me think about being an approximation theorist. And in both cases, there's the basic story, and then there's how you go from the basic story to an inducing point method. And I think the connections between these things are fascinating. And I am aware of the time, so you'll forgive me for giving a somewhat high-level perspective, particularly on the Gaussian process picture. Okay, so remember that we've put the kernel front and center in our computation. So we started off with explicit feature maps, and we pretty quickly said we don't want to think about explicit feature maps. We can build our reproducing kernel Hilbert space by reconstructing a feature map if we want to, but we're typically not going to. You don't even have to go through that construction, right? So we can do something where we say, let's build our reproducing kernel Hilbert space by essentially defining an inner product structure in terms of these kernel matrices and samples. And this actually is going to give us a Hilbert structure on things that we can write as a finite sum of kernel functions. And if you want to go to the full Hilbert space, then you need to close things, right? So you really have to find a pre-Hilbert structure. But the thing that I want to emphasize here is that if I have functions u and v that are defined in this way, then that are defined in terms of u and v being interpolators, and I want to compute an inner product between them. There's some set of points where u and v are supported, and the way that I get my inner product is by taking the evaluations of my v points, or my v function at those x points, the valuations of my u function at those x points, and taking an inner product where the matrix is this KXX inverse, right? So that kernel matrix actually serves a really central role here in thinking about defining an inner product or a quadratic form that sort of gives me the geometry of my space. So given information like that, what can I do about it? Well, remember what we're trying to do is something that, if I have no assumptions at all, is completely intellectually dishonest, right? So if I say, here's some values at a handful of points, tell me the values at another handful of points, and I don't tell you anything more about the function, well, the values at that other handful of points could be whatever, right? You know, and you can see this even in R2, right? So if I say, you know, I'm thinking of U1 and U2, U1 is 5, what's U2? The answer is you have no idea what U2 is, right? You need some assumption. So the first assumption that we're going to look at that involves an inverse matrix is going to be, let's think U1 and U2 are jointly normally distributed. And that K matrix is now going to correspond to a covariance matrix, right? So the U transpose K inverse U equals 1 is some confidence region, right? And so we've got some high probability region that stretches out over some region of my space. It's not going to be just a circle. And if I think, well, what should my posterior be, given that I have a prior that these things are jointly normally distributed, and I have a measurement of one of the things, well, the answer is that the posterior is, again, a normal distribution. The mean of that normal distribution is going to involve covariance matrix inverse times function values, so something that looks like the coefficient vectors that we've seen before, times K21. So this is actually something that looks like the kernel approximators that we've seen. But now, in addition to having some notion of how we're going to approximate our function, we also have some notion of how we're going to think about what's the uncertainty in this. And the uncertainty is going to be the covariance matrix associated with the posterior, which is a sure complement inside of our original covariance matrix. Right? So I say, I've got some prior that gives me some notion of what type of smoothness I'm expecting or what I'm expecting about the correlations between these different points. And then the posterior is going to be a sure complement inside of the kernel matrix that tells me sort of how things concentrate around the posterior mean. Okay, now I just drew things as if everything were in R2. Of course, we're actually dealing with approximation of functions. So really you should be thinking about, I've got some set of points that I'm sampling at, and I condition on those points. And the thing that I'm conditioning on those points is a generalization of the multivariate normal called a Gaussian process. So Gaussian process is a fancy word for a multivariate normal where you happen to have an infinite number of covariates, or potentially infinite number of covariates. So we've got a mean field now and a covariance kernel rather than having a mean vector and a covariance matrix. But you know, all of the computations with Gaussian processes and most of the reasoning is done with a finite set of points at a time. And so if you're not happy about thinking about this infinite collection of random variables, you can say, well, just look at a finite set of points that I might be interested in, say the points where I've measured things plus some evaluation points that I care about later. And those are going to be jointly normally distributed. Okay. So the Bayesian perspective on error analysis of kernel methods is to say we've got some Gaussian process prior with a given kernel. We're going to condition on observational data, potentially with noise, and you can incorporate that in too. And that gives us a posterior, which has some mean field and some sure complement looking kernel. And we can evaluate the posterior mean and the posterior or the predictive variance point by point relatively easily. And that gives us some notion of here's what we predict and here's what our uncertainty under this set of modeling assumptions looks like. Okay, but this still involves working with your full kernel, and we really would like to do something that doesn't necessarily involve this n by n kernel matrix. And so the perspective that people take with doing inducing point methods for Gaussian processes is what's called variational inference. So you say, I'm going to take this Bayesian perspective. What I want to approximate is this posterior distribution conditioned on observations. But I'm going to, instead of thinking about actually solving the posterior distribution or computing the posterior distribution explicitly, I'm going to come up with an approximating family of distributions, which involves another Gaussian process conditioned on some set of inducing values at inducing locations, but those inducing values are completely made up, and the inducing locations may not be a subset of my data points. And then I'm going to maximize some evidenced lower bound or minimize some measure of the distance between my approximating distribution and my true posterior distribution. And that's the variational inference perspective. And there's a number of things that look like this, the SVI and SVGP, and I lose track of the acronyms. They largely end up operating by some type of stochastic gradient descent. And this is also useful for going outside of the Gaussian process perspective. So if you want to do inference with non-Gaussian likelihood, this is a way of doing things too. Okay, so I want to spend my last 3 minutes telling you about one final story, which is the story of energy minimization or optimal approximation, which I hope we will get to the point where I can say the thing that I'm most excited about now before we end. Okay, so again, think about this simple and impossible case where we've got two things that we know one, we want to know the other. We need some assumption that we're going to use in order to answer this question. Before we said, let's look at a statistical assumption, but another thing we can do if we're given a quadratic form is to say, let's look at a ball. Let's look at some unit ball or not unit ball in this K inverse norm. So now the assumption that I'm going to have is U1 and U2 are stuck inside of the unit ball or some other ball in the K inverse norm. And now if I say, given U1, what's U2, I don't necessarily think I've got some distribution. Instead, I think, okay, I should look at the point that's smack in the middle of this interval, right? So I've got an elliptical region in my space. If I take a slice out of it with a hyperplane, I'm going to get another elliptical region. I want to approximate with the point in the middle of that elliptical region, and the shape of the ellipse is going to tell me something about my uncertainty. And it turns out that the point in the center of that elliptical region is, again, our kernel approximator. And the same Schur complement tells us about the shape of that elliptical region. It also turns out that this point in the center is going to minimize the K inverse norm of U subject to data constraints. So you can formulate the problem of finding your solution in terms of an optimization. Okay, now this is something that you may think looks very abstract, but you've probably seen before in an intro numerical analysis class. Think about the way that we talk about the analysis of cubic splines, which is one family of kernel approximators, right? So for cubic splines, you say there's going to be some kernel function, right, that's associated with solving the ODE. We've got an inner product, inner semi-product associated with the bending energy. And the way that we can reason about the error in this case is to say, suppose that my true kernel has a certain amount, or my true function has a certain amount of bending energy to it. My approximator has some smaller amount of bending energy to it. There's a gap between those two energies. If I spent all of my energy pushing up or down at one point, how far could I move it? That involves knowing about the energy and knowing about the compliance of your physical object at the point. That compliance is associated with this same Schur complement, it turns out. And from that, you can get an energy error bound. And so this is the type of thing that people do for analysis from the approximation theory side. Okay. Let me finish this thought, and then I will come back to the questions. Okay, so we've got our bound. The thing that's usually hard to compute about this bound is what is the total energy or the norm in this Hilbert space. But I want to do something that's going to, again, allow me to use a subset of the points. And one thing that I can do is to say, let's, instead of taking this minimum energy perspective subject to the constraints that I interpolate at my data points, say, what if I take the minimum energy or the minimum of this norm subject to the constraint that I'm close to my data points within epsilon? It turns out that if I do that, what's going to happen is there will be some points where I naturally hit the upper bound and some points where I naturally hit the lower bound. And those points are going to be involved in my approximation. And all the points where I sort of naturally sit in between, I don't have to worry about. I'll have 0 coefficients. So I again get something that looks like this kernel type of system where my right-hand side now involves sort of upper bound, lower bound, or somewhere in between. And anywhere where I've got a somewhere in between, I don't have to worry about the coefficient. Right? So here's a picture with more flexible bounds than plus or minus epsilon, but you can see that where you hit the top, you've got a coefficient that's negative, that's essentially pushing you down. Where you hit the bottom, you've got a coefficient that's positive, that's essentially pushing you up. And in this case, there's actually some places where I insisted on interpolating as well. Why would we want to do this? There's an adjustable cost versus accuracy knob in there that I like a lot. I don't have to worry about local minimizers, which is a problem for the variational inference methods. And I can build on the standard RBF error bounds in order to do error analysis in this type of setting. So this is something that's actively ongoing with Shinran and a few other people. Okay, so I've told you these 4 stories and taken more time than I probably should have to do it. I have a summary slide, but maybe this is actually a good time to stop and answer the questions that are in the chat.
Okay, thank you very much, David. So I'll give a round of applause for everybody. Yeah, thank you for telling us the 4 stories. That's very nice. Alex Barnett, would you like to unmute yourself so you can ask your question?
Sure. Hi, David and Alex. Thanks for an inspiring talk. I guess I had 2 questions. One is, you showed this sort of skeletonization procedure for picking a subset of points. And the question is, do you expect the number of points to have any, like, how do you expect that number to grow with the narrowness of the kernel and the dimension of omega, the space you're trying to cover? Nothing magic. So I'm kind of asking if something magic happens, or if you just basically have to place as many kernel blobs needed to cover the domain. And I guess my second question is just, like, let's say someone invents new GP methods. I found the literature very hard to get into. Do you know a software benchmarking setup where one can compare against state of the art?
Okay, so for the first question, you're right, there is no magic. The rank will tend to go up as you increase the dimension or as you decrease your kernel width relative to the size of your domain. So there's a counting type of argument, as you inferred to, that sort of gives you some notion of how many points you're probably going to need. If you're in a high dimensional space and using a not very smooth kernel, just using a low rank approximation is probably not a great idea. And there are other ideas out there. The software package that incorporates an awful lot of the stuff that I've done and my collaborators have done is called GPyTorch. This is, it's actually still maintained by a number of people, but primarily by Jeff Gardner, who's used to be a graduate student here, and then was at where he was in industry for a while, and he's now at UPenn. And that's the thing that I would compare against. It has high performance GPU accelerated implementations of most of the algorithms that I've worked on, including using the Pivotedcelestia as a preconditioner. So it does the right things. So that's where I would look for state-of-the-art software.
Cool, thank you.
We have, maybe we can have one more question. Somebody wants to unmute. I can also ask my question. Okay, so for the Cholesky, obviously pivoted Cholesky on a general matrix can be shown not to be a good idea in terms of rank revealing. I mean, you can take Kahan's matrix and then take its transpose and times it with itself, and that will be a matrix that breaks pivoted Cholesky. So what is the reason that it's working in this sense? Is it the continuity of the kernel and the fact that the matrix is coming from something underlying?
Yeah, so this in particular provably works well in the case where you're dealing with something like a squared exponential kernel, basically because the eigenvalues decay so fast, right? So there's not a whole lot of ambiguity about what you should do. And there's actually some argument about that in the appendix to the GPyTorch paper, I think. An argument about the rate of decay that you expect of the spectrum and how that's going to allow you to do Pivotedcelestia in a way that is reasonably rank revealing. If you're dealing with more complicated kernels, you're absolutely right. You know, Pivotedcelestia isn't strongly rank revealing. This is part of the reason why people think about doing things like Nystrom. So you take a larger set of points, and then you do an eigen decomposition within that, and that also works. But despite it not being strongly rank revealing in general, the squared exponential case is a case where it provably works, and so we use it.
Alex, I think that pivoted Cholesky corresponds to doing Businger-Golub on a Cholesky factor.
Yeah, there's a connection between QR algorithms.
Yeah. So I think it's Businger-Golub on the Cholesky factor.
Mm-hmm.
Yeah, exactly. And you can connect this to pivoted QR on your feature map or on your feature matrix.
Yep, thanks, Elsa.
There's actually a strong rank revealing Cholesky that Minggu has, but it may be too expensive for David.
Mm-hmm. Okay, thank you very much, David, for a great talk.
Thank you, and I'm looking forward to seeing all of you again in person at some point in the not too distant future.
All right, and maybe just we have talks now every fortnight until mid-April. The next talk is Jennifer Scott. She'll be telling us about randomized preconditioner for least squares problems. There was also a change of committee. We have some outgoing committee members like Daniel, Jorg, and Valeria, who thanks for their work and sorry to see them go. But in that, we have some shiny new committee members. Zhao Ju from UC Davis and Erin and Elsa are coming in to join us to help us organize and have helped us already organize this session until mid-April. So thanks to them, and I hope to see you again on February the 2nd at the same time. Thank you.